Working there. All right, cool. Thanks, everyone, for coming. So, well, I guess Sam already said what I'm going to be talking about, so I'll just jump straight into it. Probably everyone here knows how impressive modern AI systems have become. I've put up a few examples here of some of the things that modern AIs are able to do, from explaining why jokes are funny to GPT-3, which is one of the more advanced natural language processing systems, which can produce a lot of human-like text. DALL-E, which is an AI system that can produce different styles of artwork from text input. I don't know why we need Cookie Monster performing at Woodstock, but we've got it now because of AI. And Ghetto is a general purpose AI which is trained to do a wide range of functions, from playing games to natural language understanding and image recognition and things like that. But just because we have a lot of human-like performance and capabilities with modern AI systems, what I'm going to be arguing is that doesn't imply that AIs think or reason in the way that humans do. And I think that there is a tendency in some contexts, such as in the popular media, and even some researchers here, I've got a tweet as an example of that, to sort of make this jump from thinking that because an AI can perform certain tasks in a human-like way, that therefore it is sort of thinking or reasoning in a human-like way. And I mean, a crude example of how we know that this isn't the case is the case of a parrot, right, which can sound human, it can produce human-like speech, but obviously it's just sort of regurgitating what it's heard before. Now, I'm not saying that that's exactly the case for AI models, right? They're more sophisticated than that, but that's a sort of a way of thinking about how we might distinguish the difference between behavior and like cognition or thinking. And that's what I really want to focus on in this talk, is to help, I think, bring my perspective as a cognitive science researcher to the sort of difference between how humans think and reason and how AIs are trained to sort of think and reason. Maybe we should put those in quotes because it's rather different. So first of all, a little bit about this term neural networks, which I felt was important to discuss because most of the AIs that I mentioned, or the machine learning algorithms that are used today for many of these tasks, are based on a tool or a technique called artificial neural networks, or deep learning, deep networks, are similar terms that people use. And these are kind of inspired by the biological networks of neurons that exist in our brains. And sometimes the language gets a little bit slippery between people saying that it's inspired by and people saying, oh, you know, that's actually kind of what's happening in your brain is similar to what's happening in the neural network. But I think we need to be pretty cautious here. There are a lot of differences between artificial neural networks and biological neural networks. So without going through a multiple-hour course about how these are different, I just sort of put up two diagrams here that maybe kind of illustrate some of the differences. A neuron is a very complicated cell that there's a multitude of processes that are going on. It communicates electrochemically via the production of an action potential, which then leads to a release of vesicles that contain neurotransmitters that then transmit a signal to another neuron that it's connected to, and often there's many thousands of neurons that it's connected to, and that leads to propagation of signals across the brain. There's many different types of neurons that are connected in very complex ways that we don't really understand. Now compare that to an artificial neural network, which is each like node, or sometimes called the neuron, is really just a single unit which has like one activation value. And they're connected to each other in this very regular way. The way that these networks learn is by basically you start with some input, maybe that's an image or a sentence of text or something like that, and that's represented as a pattern of activity across these input nodes here, the ones to the left. And then that's propagated or sort of pushed forward over the multiple layers of the network until it produces an output. So maybe you're teaching it to classify images. So you put in an image as an input and then it produces a category as an output, like, well, this is an apple or something like that. So there's sort of some commonalities here. There's like a distributed series of activations over the nodes in the network, but there's a lot of differences. And what I want to do is, in spite of the similarity in the name, critically, and what I want to do is focus on sort of four key differences between, again, how humans learn and how computers or machine learning algorithms learn, and just talk a bit about those. And so the first that I wanted to discuss is the training data. So most AI models used way more training data than is plausible for humans. And the example I've taken here is from a recent paper. Don't worry too much about all the details. These are a series of fairly recent language models. The right-hand side column there is the one to look at. So each token there is basically a word that's been presented to these models to essentially help it to sort of learn to process language. And you can see that the state of the art is to use hundreds of billions of tokens. So that's like, you know, it's reading the internet effectively. Whereas humans, I mean, a crude estimate that I made is in the first 18 years of life, maybe would be exposed to about 1 billion word tokens of speech. And so clearly there's a difference of a factor of at least several hundred between how much data, like just raw data, these machine learning models are used to learn and the amount of data that humans use. Essentially, we make more efficient use of a smaller amount of data. And so that's a difference that's getting wider really every year as more and more data is sort of used to train these models. So another difference is the use of a technique called supervised learning. Essentially, to put it crudely and simplify a bit, AI models are told in many cases what the answer is that we sort of want them to learn, whereas usually humans aren't explicitly told in this way. So to take the example that I mentioned earlier about like recognizing an image, again, loosely speaking, the way that we would train a neural network to do this is give it lots and lots of examples of, say, apples. It's slightly different images, right, from different angles or different sizes or whatever. And each time we say, well, this is an apple. And then it will gradually kind of learn to extrapolate some of the features that it's associated with and kind of learn to recognize then new examples of apples that it hasn't seen before. This isn't really how humans learn to recognize objects or to learn language. I mean, yes, sometimes we will explicitly say, oh, look, that's an apple, but we don't kind of do that repeatedly in the explicit way that is done for machine learning algorithms. And in many cases, we don't explicitly say what the right answer is at all, especially with language. Humans don't sit down with their infants and teach them the rules of English grammar. It just sort of doesn't work like that. So there's a big difference there between the supervised learning, which is very common, or variants of that, in training these models, and the much richer and less well understood way that humans learn naturally. So a third difference that I wanted to discuss is a little technical here, this term called backpropagation. If that's a little scary, don't worry. This is a particular algorithm that most of the neural network AIs are trained with these days. And it's widely, well, let me hold that in a second. It's widely believed that this is not plausible to be implemented in the human brain. It's possible that something like this is approximated in the human brain, but no one really knows, and there's not really evidence for this. But let me just explain kind of what it is, right? So remember I said that many of these algorithms are trained on the basis of, here's the right answer, and we want to train the network to adjust its weights gradually so that it produces the right answer given the input that we provide it, like recognizing an image. The way that we do that is using backpropagation, which essentially is a technique where you start with the errors, how different was what the network predicted versus what it should have sort of predicted, and we push those backwards layer by layer through the network so that it knows how to adjust the weights. That's the crude idea of what's happening in backpropagation. And the issue is that it's not really plausible that this is done in the human brain. And whether or not even anything like this happens in the human brain is still contested, but certainly it's not this algorithm, which is for various reasons not plausible. And the final thing that I wanted to discuss is a term that I've sort of broadly called structured knowledge, which doesn't fully capture what I want to articulate, but I don't know that there's one term for it. The basic idea here is that humans learn richly structured relational representations of concepts and words and things and ideas. And AIs, don't really learn this way. I mean, it's a little hard to say because we don't fully understand how AIs learn or exactly what they do learn, but basically what AIs, like deep networks, learn is rich correlations and associations between different features. And humans kind of learn that as well, but there's certainly a lot more to it than that in terms of how humans represent ideas. So there's a sort of a simple example here to kind of illustrate this point. So if we think about knowledge of animals like cats, for example, humans know that a cat is a pet and it has a tail. That these are relations between different ideas that are sort of structured in a very explicit way. And of course, in reality, it's way, way more complicated than this, right? And these sorts of structured knowledge allows us to make inferences very readily, even about things that we haven't heard of before. So if I told you that a schlep was a pet, then you might be able to infer that, oh, well, it's an animal that people need to feed and things like that. Whereas AIs, I mean, they can make some extrapolations like that, but it's quite different, and there's certain limitations that have been found in virtue of the fact that they just sort of aren't really trained to form these sort of representations, at least in general. So there's more to say about all of these, but again, just to summarize, we talked about how, compared to humans, AIs rely on much more training data. Again, most of them. Many of them rely on supervised learning, which humans don't typically rely on. They use backpropagation as a training method, which isn't really considered neurologically plausible, and they tend not to form, or at least are not explicitly trained to form, this sort of explicitly structured conceptual representations that humans do. One final point, so this is, the talk that I just gave is based on an article that I wrote about a month ago, which I've just put the title up there if you're interested in kind of reading a little bit more, and there's a few links in the article to additional papers and so forth. And we still have a lot to learn about how humans represent and process information, and I think it's important for us to just keep that in mind, that as impressive as many of the AIs that are coming out are, just because they can replicate human behaviors, it doesn't necessarily mean that they're sort of thinking in the ways that humans do. So that's all I had. I don't know if there's any time for questions or if we're just done. I'm happy to chat afterwards if anyone wants to either.
Beautiful. Thank you so much,
everyone.
James Fodor.